No, just give me just a second. There. Can you see the screen?
Yeah, I can see that.
All right. Yeah. So 5.5 through 5.7, they're all word problem stuff, and this first question's the epidemic stuff. So just looking through it, suppose for a certain disease described by the SIR model, it is determined that A is 0.003, B 0.5. In part A, in the SI phase plane, sketch the trajectory corresponding to the initial condition that 5 people are infected and 784 people are susceptible. Okay, so I'm sure you can just get this by kind of guessing and checking here.
I educated guessing. It's your D.
Yep. So the reason for that is that the horizontal axis, the susceptible, and then the vertical axis being the infected, the more people that you have susceptible, the more potential there is to be infected. And it's also going by the initial conditions. So the initial conditions, 784 infected and are susceptible. 5 are infected. That's this point right here, right? It's 784 and 5. So very, very close to the x-axis. So it could only potentially be D or B, but it can't be B because it's not going to explode like that. It's got to be this one. Okay. Good. And then from that, choose the correct answer below. From the graph, the peak number infected person is blank, which is a close match to the theoretical. From the graph, the peak number of infected person is blank, which is not close to the theoretical prediction. So the theoretical prediction it gives us here, right, it's 167 persons when the epidemic is at its peak. But notice that our peak is like up here, if we blow up a little bit. So our peak looks like it's around the 400-ish range. Mm-hmm. But the theoretical peak is at 167, so they're not close. But what number do we type in here? Let's see. I think we just have to make an educated guess.
Yeah, it says like B over A. So would that be the 0.5 over the 0.003 kind of thing?
I think that's the 167.
Okay.
I think.
Yeah, that's where the 167 came from.
Yeah, the number that we need to plug in is the vertex of the graph here, the maximum of the graph. They're going by 50s, so this is like a little bit above 350. I'm going to try 360. Nope. Okay, so maybe that's not going to work. Maybe you have to actually use the equations to do this. So let me find the equations for the SIR stuff. I have in my notes here. Yeah, here. All right, so the 3 equations that we care about, capital S prime is negative SAI. I prime is SAI minus KI. R prime is just KI. So that B that they gave us in the question is, I think they just write it a little bit funny. Let's see. Oh, that's the K value, I think. I wrote it as K in the notes, but I think the B value is the K value that they have, the 1 over K value. Okay. I'm blanking here. I don't know what to do. Read my hint again. Refer to the graph and estimate the peak value. Yeah, we already have the theoretical prediction. I really do think they just want us to
There's
look at the graph.
question help. There's an example.
I think it's just going to say look at the graph.
Yeah. Well, it has into the equation I equals negative S plus 812. I don't know where 812 came from, but
Yeah, that's coming from all this stuff up here, which is how we graphed it initially.
I guess it would all be the same, but change the 801 to whatever your initial is.
Yeah, mostly.
And then just where there's an S, just put 167.
Mm-hmm.
7 plus 812 plus 100 divided by 3 ln 7 divided by my number is that didn't work.
Where are you getting 7 from?
Oh, my number is 756.
Oh, okay.
390. That looks right for mine. See if it is. Dude, my answer was 340.
Okay.
That formula didn't work.
All right, so yeah, it looks like what they do is they actually solve the thing. So let me write down my equations again. So the A is given, and then what was it? K is B over A? Yeah, K is B over A. Which for us, or at least in my example, that B over A, that's the 167-ish. Right? Cool. So then plugging in all of those constants, S prime is going to be equal to, for me, A was negative 0.003, I think. Yep. 0.003 SI. I prime would be A 0.003 times S minus K over A, which is B, so 0.5 I. And then R prime would just be K, 167 I. And then this one I'd have to distribute that 0.03, so 0.003 SI minus, what's 0.003 times 5? 0.0015, I think, I. Cool. So then we just have to solve this using the stuff that we were using before. So the stuff we were using before, we'd have to like move it all over to the right-hand side. So S prime plus 0.003 SI is equal to 0 for the first equation. I prime plus 0.0015 I minus 0.003 SI. And then the last equation, R prime minus 167 I is equal to 0. So just moving everything over to the left-hand side. And I think some of these are going to be easier to solve for than others. Let me just see the way that they did it. So what they did is that they did the ratio of some of this stuff. So if we look at the ratio of the differential of I with the differential of S is what they do here. That's just going to be solving the I, which was solved for, solving the S, which was solved for, and then just dividing those two things. So just think of it as I prime on top as the numerator. So I prime was 0.003 SI minus 0.0015 I, and then S prime as the denominator, negative 0.003 SI. Then dividing both of these by that negative whatever, we get negative 1 plus what's this? Negative 0.0015 divided by 0.003? Is that 2? Or is that 0.5? I think it's 0.5. And then 1 over S. Yeah, okay. So I know this seemed kind of weird to do, doing the ratio of the differentials, but that's what they did. So they took I prime divided by S prime, and it came out to be this, which doesn't look too bad. All right, let's see what they did next. Okay, so now what they did is they just solved this as is. So this is a separable differential equation at this point. So we're going to break it down to be di on the left-hand side, and we're going to multiply over. What's a better way to write this? Like that, maybe? Multiply the ds over to the right-hand side. And then we anti-differentiate. So this is just a 1, which anti-differentiates to be an I. But the right-hand side, negative 1 is going to change into a negative s. 1 over 2s is going to change to be plus 1/2 natural log of s. And then there's a plus c that I have to throw in there as well. Okay? So that's that part. Initial conditions now. So that's going to be used to find the c. So if we plug in initial conditions, remember that when the I was, for my example, the I was the infected. So I started off with 11 infected people and 801 susceptible. So I'm going to plug in 11 for the I and then 801 for the S.
Where do you see? I see. 4 people. Okay, so 4. I equals S.
And I don't have a calculator in front of me to figure out what my C is going to be equal to at this point. I need to go find a calculator. I'm sure I have one in the house somewhere. I'm getting 809 from Google.
That's your C.
As my C, yeah. Rounding it to whole numbers because we're talking about people.
745.69. You got it. 746.
747?
745.69.
Oh, yeah. Okay, so 746, yeah. Okay, so this thing that we just solved for, this little I here, just writing it back out, I is negative s plus 1/2 natural log s, and now it's plus 809. This little I that we got, this represents the ratio of infected people to the total population. So now to get capital I, which is the actual number of people that are infected, we're going to multiply by the population size n. So we're basically just going to multiply everything here by n to get the entire population size. I'm just seeing what they did at this point. Oh, I think I see the problem. Sorry. When we solved it for little I and then tried to find the constant C, we should have multiplied by n first, because this is dealing with proportions, and the initial conditions that we were plugging in were whole numbers. So, oops. That stuff we just didn't work. We need to multiply first by n. So that's going to change this I to be a capital I. It's going to change this proportion S to be a capital S. And then plus whatever n is times this 1/2 natural log S. Plus, and then this C, we're just going to keep it to be a constant C. Now we'll plug in the initial conditions. The problem is that I don't know what the capital N is. It says 500. Does it say 500 somewhere in the problem?
No.
I wonder where they're getting this 500 number from.
Space.
I think what they're saying is that for that thing out in front, you just want to take the B value and divide that by the A value. Since this just becomes like the K, I guess. All right, but now we can do the initial conditions. 11 is, for me, negative, was it 801? Oh no, sorry, 784. Oh, I was doing the example and my problem at the same time. I have 5 infected people and negative 784 susceptible people. Plus whatever 0.5 divided by 0.003 is, natural log of, and this is now a capital S, I think, or it might stay lowercase s. Oh, crud. Nope, capital S. So 784. There we go. That's how we want to figure out what our constant C is. I'm typing it into a calculator here. I'm getting a big negative number.
Yeah, I did too.
Negative 326. Oh, they just, yeah, they left it as as whatever it is, the natural log thing, which is fine. Okay, and that's it. So that means that we have our solution. I is negative S plus whatever this is, natural log of S, minus that 326 number. Okay. So this is the equation of that graph that we selected for D. Now, if we want to maximize this, I think we just have to take the derivative. So let's see if that's what they did. Oh, they just plugged in that. All right, so that prediction that they got, the 167,
Plug that in.
plug this in for the S.
That didn't work.
Was it close? Are we just off because of rounding, or did it like not work at all?
It just said no, and it gave me the same reason that it gave me when I was actually wrong. Because I came out to be 333. It looks right, but
So you typed in 167 for the S, and it was 3 what?
332.99, so 333.
Was that for your numbers or for my numbers?
for my numbers.
Okay. Let me do my numbers here. I got 360. And I already tried 360. That was my guess from before. Oh, but that's right. But we have to select the other one. Sorry.
So it is close?
It is close, yeah, because that's what the graph looks like, right? It's around 360. So I had the right number from before. I just selected the wrong thing.
Yeah, that worked.
Okay. Whew, that was a lot. All right, I'm going to talk through it again. So our three equations for SIR. If we are graphing the I with respect to S, what we can do is we can look at the ratio of the differentials di, ds, and just think of this as I prime divided by S prime. So we have I prime and S prime solved for up here, and we're just going to take the ratio of those two things and we get this. Okay. Then this, unfortunately, is the lowercase I and S after we solve it using separable differential equations. So we have to multiply it by the population size to get back to the actual I, the number of infected, the number of susceptible, all the way down. Okay. From here, we use the initial conditions of when we know a certain number of infected to a susceptible to find the constant at the end. This, we could then graph, just thinking of the S as the independent variable, the I as the dependent variable, and get the graph for it. That's the graph for part D here. After that, this next part is not necessarily stuff that I'd shown you yet, but this part, compare this with a theoretical prediction that S is 167 persons when the epidemic is at the peak. So if that's the theoretical prediction, that's the X or S location, 167, we plug that into our equation to figure out the number of infected at that particular peak. So there we go. Whew. That was a hard one. We lost Robert. I think I frustrated him. Hi, Valerie.
Hola.
Do we want to look at number 2?
Sure. It's the next one.
Yeah, so this is a spring one.
Oh, gosh.
So this is the double spring problems here. So 2 springs and 2 masses are attached in a straight line on a horizontal frictionless surface, as illustrated. The system is set in motion by holding the mass M2 at its equilibrium and pulling the mass M1 to the left a distance of 1 meter, and then releasing both. Okay, so it's got a bunch of stuff here. So let me get to my system stuff. Let me get to the next page of my Word document here. All right, so when you're dealing with 2 springs that are connected together, there's 2 differential equations that you have to worry about. And I wrote these out in that video I made on this, but it's also in the book as well. So you can either just have this written down somewhere in front of you, or I don't know, whatever. But it's this. So let me just write it all out. Okay, so these are the system differential equations here. Let me see if I can get that to the side and then the homework problem. There we go. Okay, I think there's just a little bit of a problem here, and that's how the M1 and the M2 are labeled compared to this system that we have. I actually think it's backwards, and we may need to rewrite these based on this problem. Because on the problem that I did, and the more generic problem, is the one where it's connected to the wall on the left, and then M1 is the first mass that's connected, and M2 is the second. So now that I'm really looking at it, I don't think we can use these. Or we can use them, we just have to rearrange the M and the Ks, and it's just going to be too much of a nightmare. I think it's best just to start over. So the way to do these is to separate them out into the 2 different masses, and let's focus on mass 1 first. If we're looking at just mass 1, only one thing is interacting with that mass, and that's the K1 spring. So the force that's acting on mass 1 is going to be a positive K1, and we have to be careful about the x value because the x value, is really going to be the difference between the two. So the difference between the y and the x value. The difference between the y and the x value you can think of as how stretched or compressed the K1 spring is. All right, so that's the only thing acting on mass 1. For mass 2, there's two different things acting on it. The first thing acting on mass 2 is you can think about the K1 spring. So that's going to be acting on it, but in the negative direction, the constant K1, and then again that y minus x distance. But it's also going to have another force acting on it on the right, which is the spring that's connected to the wall. That's acting on it from the right, K2, and we're looking at the distance y that the spring is. And it might have to be negative. I have to think about it. I think it is going to be negative. It's going to be negative because when the mass is moved to the right, a positive y value, the spring wants to push it to the left. Which makes me think that this should be a positive value for the same reason. Because it wants to push it to the right. Does that make sense? This may need to be
Let's do it.
negative as well. Sorry. Yeah, I like this better. Okay, so going back to mass 1, this has to be negative because it's trying to push it to the left. So the force is acting in the negative direction. So then these have to be fixed that way. For mass 2, spring 1 is pushing it to the right, spring 2 pushing it to the left. Okay, so let's go with that, and from there we can come up with our system. Because our system is going to come from Newton's law, so we're going to have two equations. The first equation is going to be m1 x double prime, which is the mass times acceleration for the first mass, is going to be the only force acting on that, which is the K1 y minus x force. Newton's law for the second mass, mass times acceleration, is going to be the two forces added together. So the K1 y minus x minus the K2 y, just combining these two forces that are acting on mass 2. All right, and then we can multiply this out and kind of combine stuff together. We'll combine the K's together. We'll have a K1 minus K2 that's acting on the y. And then we're going to have a negative K1 acting on the x. Okay. And then this one we can multiply out as well. Just negative K1 acting on the y plus K1 acting on the x. All right, I like that. So now we could rewrite this into our generic term for a system of equations by getting all the x's together, the y's together, and then equal to 0 on the right-hand side. So just for my first equation here, I'm going to leave the m1 x double prime on the left. I'm going to go ahead and subtract the k1 x over there as well. And I'm going to add the k1 y over, and then it's equal to 0. The second equation, I already have the, I want the x's first. So I'm going to add that k1x over to the left-hand side. That's my only x value. Plus I have the m2y double prime and minus k1 minus k2 times y equals to 0. Okay, I'll let you guys get that done. Oh, good. There's a viewing example. Let's double check to make sure I have my stuff in the right order, my signs.
It says F1 is all positive, F3 and 2 are negative.
I think we're good. Oh, we're not good.
It's pretty funny how it says 37 parts remaining.
I know, it's a long problem. Okay. I think I had my signs the right way the first time. Oh, that makes me mad. Alright. Sorry about that. It looks like I did have this one right. But again, the sign out in front should have been positive. Same thing here. These should have been a negative. This one should be negative as well. I had that one right. Okay. So, some of my signs were wrong. So we fixed them. And this is the system. M1 x double prime minus k1y plus k1x is equal to 0. For my other one, m2 y double prime plus k1 plus k2 y minus k1x is equal to 0. All right, so those I'm just copying over from here. So for those of you watching the video later, just go back and fix the signs here. They do have like a really good explanation here in the view and example on why which ones should be positive and which ones should be negative. I just had them in the wrong order here. So for mass 1, this should be a positive force acting on mass 1 from this first spring. And the reason for that is because usually the y minus x value will tell you if it's compressing or stretching out. And these are backwards as well. So this one should be negative, k1y minus x, and this one should also be negative, k2y. Okay, but after plugging those in, so these are now all messed up with the signs, we're here. Is that all right? Is that okay? Explanation enough so that we can just solve the equations? Okay, because solving the equations are a little bit more important to me than setting up the problem. Most of the time the problem is set up for you. But definitely I would recommend reading through the section itself and going back through these processes of when the forces should be positive or negative. I was just confused because the problem is set up backwards from what I'm used to. Okay, we want to plug in the constants that they give us. So my M1 is just 1 kilogram, so I have 1 x double prime. Minus k1, which is 5, so minus 5y, plus k1x, so plus 5x. For my second equation, m2, which is 4, y double prime, plus k1 plus k2, which is 5 plus 21 fourths, which is 41 fourths, I think, minus k1, 5x. Okay, and then so from this point, we just solve it the same way we were solving stuff earlier in chapter 5, which is changing stuff over to those differential operators. So my first equation here, I have an x double prime, which I'm going to write as d squared, d squared applied to x. All right. Oh, my x is in the wrong spot, sorry. Oh, geez. That's what I get for copying it down from the thing and not thinking about it too much. D squared minus 5, or plus 5. Right, so the d squared, that's the x double prime, but I also have a plus 5x. So just moving that over and then writing the operator like that. For my y's, I have a negative 5 acting on the y, and that's it.
So if my M1 is a 2, would it be 2d squared plus 5?
Yeah. For the second equation, the x's should be first. So we have a negative 5 acting on the x. plus we have a 4d squared plus 41/4 acting on y. Okay, now what we want is we want to eliminate either the x's or the y's. Doesn't matter which one we eliminate. It's looking like the x's will be easier to eliminate because of this awful looking thing with this fraction here. So what I'm going to do is I'll eliminate the x's by multiplying equation 1 by just 5 and equation 2 by that d squared plus 5. So now equation 1 is going to be 5 times the d squared plus 5 acting on x, minus 25 acting on y. The second equation is going to be kind of awful looking for a little bit. Negative 5 d squared plus 5 acting on x, plus d squared plus 5 times 4d squared plus 41/4 acting on the y equals 0. All right, so that's just adding a 5 onto every term in the first equation, or multiplying a 5, sorry, and then multiplying the d squared plus 5 onto every term in the second equation. The reason we did that is now we have the same operator on the x, just negative, so now we're going to add these equations together.
Why do we need the second 5?
What do you mean the second 5?
Well, why couldn't we just do d squared? Okay, never mind. I see it now. Okay, never mind.
Yeah, because there was not a 5 on this one,
Okay.
so we had to multiply a 5 there. There was not a d squared plus 5 here, so we had to multiply the d squared plus 5. That way they're the same thing, but opposites. So when we add the two equations, the x's cancel, and my y's are going to be negative 25 plus this awful looking thing. And that whole thing acting on y is equal to 0. So the negative 25 plus these two operators multiplied together, all acting on y. And then we have to multiply this awful thing out. So we still have the negative 25 out in front, plus foiling this all together. It's going to be the d squared times the 4d squared, so it's going to end up being 4d to the 4th, d squared plus the 41/4 plus 5 times 4d squared, plus 5 times 41/4. I think that's 205/4. And combine like terms. I need a calculator now.
Is my y supposed to equal 0?
There should be a 0 on the right-hand side of the equation, but the y shouldn't come out to equal 0, no.
Oops.
I think this is, I'm trying to do it in my head, 105/4?
What did you?
I'm trying to add the constants together, the negative 25 and the 205/4.
Oh, you add them together. That's what I did.
Yeah, 105/4.
Okay, cool. So I'm here. Next thing you want to do is to get rid of all of the operators. So this will be 4y quadruple prime plus 121 fourths y double prime plus 105 fourths y is equal to 0. I'm going to multiply everything by 4. I'm sick of these fractions. Okay, so I have this equation now. It looks really awful, but it's very easy to solve because this is a homogeneous equation, which means that we're just going to do auxiliary stuff. So really, we're going to do 16r to the 4th plus 121r squared plus 105 is equal to 0. I don't know if that can be factored or not. I hope you guys have fancy enough calculators that can do the quadratic equation at this point.
I'm still using my stupid calculator, I guess.
That's okay too. Just plug it in. Oh, I forgot to make it a fraction. Cool. I cheated. Oh, sorry, it's not 2. By 32. Does anybody have a calculator that can save us?
Oh, it's 121. Okay. That makes sense.
Inside the thing, it's 7,921.
Thank you.
Yeah.
Does that simplify down?
89.
Okay, cool.
So it's 89 over simplify. Yeah.
You can at least add them together and subtract them. I got -1 and subtracting them.
-105 over 16.
-105 over 16.
Yeah.
Oops. Undo. Okay. That's interesting. Is that really the right answers? Did I mess up somewhere?
That's what I got, so.
Okay. We have to take the square root now. So because this was a 4th order auxiliary equation, r squared is equal to these two things, which means that r is going to be plus and minus I is one set of solutions, and then plus and minus whatever the square root of all that stuff is. I. So I'll just write it as square root of 105 over 4. Which means that we have 4 different solutions, and we're just going to add those 4 different solutions together. Remember that we were solving for y. So we're going to have a constant times the first solution, which is the I auxiliary solution, which is just cosine of t. Right? Plus, we're going to have one for sine of t, for the negative part of it. All right, plus we're going to have one for this awful looking one, which will be cosine of the square root of 105 over 4t. And then we'll also have plus a constant sine of square root 105 over 4t. All right, so this is my y solution set. But we have to figure out what these constants are, and we can't really figure out what those are yet until we figure out what the x solutions are. To figure out what the x solution is, we have to go back to the beginning, to our system of equations, and solve one of these for x in terms of just y. And I can do that with my second equation. Let me look at these instead, the ones that have numbers plugged in. So I just have to solve this one for x. All right, so now we need to find x of t using, this was the second equation from our differential equations. We're just going to solve that for x. So here I'll just add it over and then divide everything by 5. Since I know what my y is equal to, I can just plug that into this equation now to figure out what my x is equal to. Unfortunately, I have to take the second derivative of this thing and plug it in here. So let's do that. The first derivative is going to be negative c1 sine of t plus c2 cosine t minus that square root thing, c3 sine of the square root thing, and then plus the square root thing, c4 cosine of the square root thing, t. All right, so that's just the first derivative of y. Now the second derivative. All right, so then it's just the derivative of the first two terms. Those are easy. The derivative of these terms is going to bring out another of those square roots. This one's going to stay negative. It'll be 105 over 16 now, c3. And now it's cosine of that square root thing. Same thing here, but now it's going to be negative again, 105 over 16 c4 sine of the square root thing. Okay, now we can plug it into our equation here. So x is equal to 4/5 times the second derivative here. Okay, that plus 41/20 times the function itself, which was up here. I'm praying that a lot of this stuff will combine together. I'm sure it will. Yeah, so I have a Oops, this should be C1 here. I wrote C2. I have a C1 cosine t, and then a C1 cosine t. I just have to worry about the coefficients out in front. So this is negative 4/5 and plus 41/20, which is plus 21/20 C1 cosine t. Same thing for the next one, plus 21/20 C2 sine of t. All right, and then these are going to get awful. I'm definitely going to need some help with these. So we need to distribute the 4/5 onto the 105/16, and that's negative. And I need to add that onto 41/20. Google says it's 3.2. What is 3.2 as a fraction?
Uh, 16/5?
16/5. Okay, I like that. C3 cosine of that square root. 105/4t. All right, and the other one should be pretty much the same thing. So also negative 16/5, but C4 sine of the square root 105/4t. Okay. Whew, oh, and there's x. We did it. I should have started back here, huh? Oops. These just wanted the equations. So I'm scrolling up, sorry. Let me plug in my equations here. Oops. Oh, they want it in terms of the K's and stuff. Ugh. I probably should have done this first, just to make sure we had the right equations. No, we're good. Okay. Yeah, now it wants the actual things. Okay, unfortunately we're not done because we have to figure out what the constants are based on the initial conditions. So remember that we had two sets of initial conditions. We had the starting location of x, which was the first mass. So reading back through the paragraph, it says that the first mass was just held in place. Right? Oh no, sorry, the second one was held in place. The first mass was moved a meter to the left. It was not given an initial speed, so the derivative of x is just 0. My second mass was held in position, and it was also not given an initial speed. So I have 4 initial conditions because I'm trying to solve for 4 different constants. Unfortunately, we're going to have to take another derivative of x. All right, one last derivative.
I'm gonna die. we take the derivative enough times, it would just be 0. Let's take all of the...
It's funny that it's taken like a half an hour already.
I know, these problems take so long.
You gave us 4 of them.
And how many of them are on the test?
Not very many.
All of them.
No.
Hey, you said that last time, and all of them were long for me. You saw that.
I did. I double checked this time to make sure that they were not all super long and awful.
I got screwed over that last test.
Noah put y equals in place, he said.
I think I did the derivative right here. Okay, so let's just plug stuff in. So plugging in that first thing, x of 0 is equal to -1. That's going to be -1 on the left is equal to, when I plug 0 into all of these cosines and sines, only the cosine is going to give me a 1. All of the sines are just going to disappear. So I end up with 21/20 C1 from this first term. That's 0. Here, I'm going to end up with -16/5 C3. All right, so that's one equation. My next one, x prime of 0 is equal to 0. That's going to give me the equation 0 is equal to 0, 21/20 C2 plus square root of 105 C3. No, minus, oh, geez. Sorry, I did not do my thing right. This should have been a sign here. Okay, but this is the other equation. I get 0 on the left, 21/20 from this term, and then negative square root 105 C4 from the last term. All right, more. Now looking at the y's, when y of 0 is equal to 0, I'm going to have 0 on the left. I'm going to have to scroll up to figure out my y equation, which is way up here, to this one. If I plug 0 in for this one, I'm going to get a C1 and plus C3. And then finally the last one, plugging 0 into the derivative of y, 0 on the left, and then the derivative of y was here. I'm going to get a C2 plus a square root 105 over 4 C4. So C2 plus square root 105 over 4 C4. So I have these 4 different equations to solve my C1, C2, C3, and C4. Great. And now we just do it. I'd probably start with this third one, because this third one gives me that C1 is equal to negative C3. And I can plug that into the first equation. Because that's going to give me -1 is equal to 21/20 negative C3 minus 16/5 C3. All right, combining those together, that's going to be -1 on the left, negative 69/5 C3 on the right, which says that C3 has to equal to 5/69. Great. Which means that C1 is equal to negative 5/69. Okay. Now for the C2 and C4 stuff. I'll start down here. looks like C2 is equal to negative square root 105 C4. And plug that into here. 0 is equal to 21/20 negative square root 105 over 4 C4 minus square root 105. C4. The point of it looks like, is that C4 is just 0, though. Because there's no way that these are going to cancel out to be nice. C4 has to be 0. It's the only way that it makes that to be 0. And if C4 is 0, then C2 is also 0. Cool. That's a little bit nicer. That means I have these two for my system of equations. X is. All right, so it's only the C1 and the C3 that I care about. So from this equation, C1 was negative 5 over 69. So I have the 21/20, negative 5 over 69, and that was on the C1 cosine t. All right, I also have a C3, which is positive 5 over 69. That one goes here. So minus 16/5 positive 5 over 69. Oh no, sorry, the C3 is gone. And the C1 should have been gone too. Cosine of, this was the square root 105 over 4t. Great. So that's x. We can multiply these fractions together. Y would be the same thing. So y would be plugging in the C1 and the C3. So it looks like it's C1 cosine and C3 the other cosine. So negative 5 over 69 cosine t. And that's going to be plus 5 over 69 cosine of that awful square root one. All right. And then we just type it in and hope for the best. Do those simplify down to be anything nice? Probably not.
The first one is negative 16 over 5.
Really? For that?
That's yeah.
That doesn't look right.
No, I'm sorry. negative 7 over 92. My bad. Sorry.
Negative 7 over 92. Okay. That one's on cosine t.
Yeah, you're right. And then the second one is negative 16 over 5.
No, the 5's cancel.
Negative 16 over 59. I'm sorry. I'm looking at my calculator wrong.
Okay.
My bad.
It's okay. All right, so double check, make sure I type that one in right. And there we go. I mean, we don't have to actually check the answer to make sure it's right. Because I did it, which means it's got to be right. I'm too scared to hit the button.
I don't know. Yeah, I don't know if we can trust your answers nowadays.
You have a check thing above saying show completed problem.
Oh, what?
Yeah. That's the answers we want.
There's the right answers.
We need that button.
So there's the right answers.
Why?
I mean, you can see that we were close. It's just the numbers out in front that were wrong.
That says close,
Horseshoes and hand grenades.
and that looks like a hand grenade.
No, come on. It had the cosine t term and then the cosine with the square root term. And then, yeah, same thing down here.
69 over here, and you have 43s over here.
Well, I know, but I'm blaming you guys because you're the guys that told me the numbers. It starts way back up here, right? Because this was the square root that you told me was the answer to the auxiliary
I
thing.
think it goes higher than that.
Yeah, mine was 165 over 6.
It all stems from this square root right here. This was wrong. But if that wasn't wrong, everything else we did was right. They're hard problems, and I know they take forever.
They do. Okay.
I made sure that the test does not have these.
That's good.
I mean, it has maybe one.
That's different than doesn't.
It's probably got 6 or 7.
No.
That's way different than I made sure the test doesn't have one of these.
Yeah,
Oh,
I
wait,
said
I think there's one.
I said it wrong. It doesn't have many of these.
Oh, as long as it's not this one.
It shouldn't have any.
I don't know.
So if it's one spring, it's okay, but why do we need 2 springs?
Especially if it takes 45 minutes to do and we only have 180 minutes.
I know. It took me a while.
And then you still gotta run it. That means you gotta do it again.
It's 2 pages.
It was a lot.
Problem.
Yeah. It's a big problem.
Oh, dude.
But now you know how to do it, at least for the homework question.
You know how to do it wrong.
If I had a calculator.
Why am I...
The
Okay.
question is, why doesn't a math teacher have a calculator?
I do. They're all downstairs. I just always forget to bring them upstairs. I think the problem is that I don't ever use a calculator unless I'm working problem with you guys. Like when I'm just going through my notes, there's no numbers really in my notes.
And you copy this stuff from the book.
Yeah. So like all of the calculations are all calculated for me. It's just
Cheat.
knowing the
The book
process.
could be wrong too.
It could be.
So,
I trust it
there's
though.
another one. I think we should do number 3.
We don't have time now. I'm like way over.
Okay.
Oh gosh.
Yeah, there's another one.
This one separates it out a little bit better, at least, because it gives you the solutions here. The problem is that it also adds in an external force.
What kind of them?
Yes.
But at least it has the solutions.
Yes. And it has parts. Well, I don't know if parts are better.
I think they're better. It separates the problem out for you a little bit. And here you can just watch the video and see the completed problem and the right answers.
Or if we get it wrong enough, we can just get them that way.
You know, it's like everybody else does it.
Okay.
All right. So you have this stuff due next week, and then the test is also due next week
Okay.
for chapter 5.
So much.
And then chapter 7's coming right after that. Hey, did you get my email about the thing going on tomorrow?
I did.
I did. I'll be at work.
Okay.
I'll be there. I'll try to. I'm not gonna try. I'll be there.
Okay.
I might be able to call in, but I won't be able to speak or anything.
Yeah, bring up a question like this for her.
Oh my god, she's gonna hate me. She's like, I don't even have a book.
Yeah.
Wait, who are we asking? This might change.
Kate Morgan. Kate. She works in the ACA, the Academic Skills Center, ASC.
I don't know who that is, but
Cool.
I will find some challenging things.
All right, thank you, Mr. Leeser.
Yeah, of course.
Okay.
See you next Tuesday. Bring more questions. We'll do number 3 on Tuesday.